Welcome everybody to our class on DESeq, where we are going to do multiple comparisons. In the last class, we just compared condition A and condition B. And today we're going to do something that's more common, where you want to compare a bunch of samples back to one condition. And then how do you deal with all those results? When you're making all those comparisons, how do you extract them? And so we're going to rehash our skills, use them to do a real quick big diff. And then really a goal here is to figure out how to export all those results into a data frame that you could use moving forward. So let's do that. And starting here in class 2023, we are in 05 R analyses, RNAseq, 01 differential expression, and 3 DESeq, diffing all the conditions and then how to re-import them. If you're taking this on the web at long-non-coding-RNA-io.teaching, we are here in RNAseq classes here. And once we finish this, we'll put all of these skills together and do a bunch of analyses with 480 DNA binding proteins. The next section. Okay. So we're getting set up here. I'm on the code in my RStudio. And let's start by loading our packages and environment. We'll need heatmap. We'll make a heat map today. DESeq, ggRepel just to move text around. And I'm just going to load my color scheme here. I believe you all have the same thing there. And then we can unload our environment variables. This is so handy. All of our hard work has just been, now takes about 2 seconds to get to, and we're ready to do DESeq. Okay, so one of the first things we need to do is factor our sample sheet. So currently our sample sheet has a column called condition, which has a unique entry for each of the conditions. That's what we're going to factor. And we have a lot of samples, so we have to do a lot of factoring, but it's key to remember that this first position is the most important here. And that's going to be our denominator for all the other comparisons to that denominator. And so here, what we're setting up is to do total RNA compared to cytoplasmic, compared to nuclear. And so total should be the average of all of them, or you can think of it like an input in chip data. And we're going to see which genes are enriched in the cytoplasm versus that are more present in the cytoplasm, so they show up over total there, and the same for each fraction. So all we're doing is factoring just with a lot more levels. Note that we have this concatenate here to make it a string. And so we're going to set our levels. There we go. And now we'll see in our sample sheet that our condition is factored with 5 levels. Okay, so I think I've highlighted enough how important that is. And then we're setting up our input as we have in the previous classes. The count data is all of our counts now. We're using all the samples. Call data is a sample sheet, which has the factors based in condition here. And the design file is on the factors that are in the condition column. Okay, so set up that matrix and convert it to integer mode, which we did in the last class, but it'll do it for you. We have we're ready to go here. So we'll run DESeq on this DDS we just created above. And again, this is going to take a minute because we have a lot of samples going on here. But again, I just cannot believe how fast this is compared to all that it is doing. And so we're making all of our comparisons, and we're just about done having it run here. And then what we're going to do is look at our results. Last time it was easy. We only had one result, nuclear versus cytoplasmic. But now we can see if we do result names, which is another DESeq function. We used rlog assay to grab up rlogs, DESeq to run DESeq. Result names is another one you'll use commonly. And we always want to get rid of this intercept. It's in those documents I mentioned, but not really worth going into. And so we have our comparisons here where it said Homo sapiens nuclear versus Homo sapiens HepG2. So we're basically doing nuclear versus total, cytoplasm versus total, insoluble cytoplasm versus total, and membrane versus total. Obviously, we didn't do total versus total. So there are our result names. And in those results, for each one of those results, we have that table of log_2 change between the conditions, the p-value, all the good stuff to go start finding your favorite genes. And so we just took a look at them. And if we wanted to just say, we want to look at one of these tables, we can go into using results. This just gave us the names. Results is going to actually extract the results from the Deseq DDS here. And the name we want to pull out is this condition that we got here. Just copy and paste it. Okay. And so now we have results for that. And then if we make it a data frame, which I'm guessing, yep, that's exactly what we're going to do so we can look at it better. We're going to make it as a data frame, move the gene ID to columns and merge in our gene names. We don't just have to look at that ensemble ID. And I'm just going to use a mutate here to add a column result name and change this to a little simpler text. Okay. It's nice having all these tidyverse skills that we have, so you can just quickly read through this now. And you can also do it stepwise if you want to pause and go back over those things. Okay, so we made it our results as a data frame, and row names, the column, merged it. And so now if we look at our ResDF, which is the thing we'll want to save in the end, and we don't have to do any of this again. This is just for one condition. So now we need to do this for all the conditions. And if there's a lot of conditions being compared to, you're definitely going to want a for loop. And that's where we're going with this next. But we have in a given entry all of this information, the base mean about how abundant the gene was, how much it changed between the conditions, whether that was significant. And now we have the gene name, and we're keeping track of the result name as well. Okay. So we can then also index into this if we want to do summarize of the log fold change. It does show us that we have some NAs in here, so we might want to be cognizant of those. But again, so here's result names. We are just saving it to kind of go over that again, but really we just looked at them. So there's multiple tables in that DDS of results. And so now we want to get all those back out. And if we take out the first column here, so we're indexing with a -1 to remove the first column, which is intercept. And now if we look at our result names, we don't have the intercept anymore. Again, not worth going over, but you don't need the intercept. Okay, so this is a common practice. And we can see here that let's say we had 100 comparisons. And what we want we know what we want for each of those comparisons. So we can set up an empty data frame with all the values we want out of there and do a for loop to read in and start merging the information into those columns. So we're setting up a results data frame here. We're just doing data frame function. This is just going to be absolutely empty. But what we're saying is make a column called gene ID, the base mean, and really these are all the same things that are in our ResDF here for that one condition. We're basically just taking the names of the columns. Not a big deal. Okay, and this just looks like a lot, but really they're just all the column names. So we can do that. And we're saying what we want them as is if they're a number or a character. That's always a good thing to do. You know, you can change it later with mode function that we went over. Okay, and we're also going to make the same data frame for a shrunken log fold change. This is something you might want to do and is really important that, again, we're worried about those values that are coming from low abundant transcripts. So what it's going to do is make the fold change shrink as the abundance of the gene goes down. It's going to normalize it. So it's a more conservative way of doing this. And so I want to keep track of those shrunken log fold changes, but I need to keep that in a separate data frame. So I'm going to set up the res shrunken data frame here. And then so now we can populate this quite easily. I have it all written out here for you, but we can go through it. Is that we're going to go through 1 through length result names. So we know currently that is like 4 or 5 of the comparisons. We have 4 comparisons here. And then we're going to say the result name is the names of I. So this will give us the result names. And then we're going to do results DDS, which is the same thing we just did for one example. And we're going to say the name equals result name, which we just made here. So we're going to say for basically for each of these, go through and give me the DDS for the results for that name. So it's just going to go get the table for this name. And then for the res shrunken log fold change, we have to run the shrunken log fold change function. And so we probably should have done that up front separately, but we're going to do it in the for loop. So for each of these results, it's going to do the log fold shrunken conversion on our log fold change. And this is the coefficient is the result name. So it's going to look at the values for that result name. So it's really just looking in this table and normalizing the shrunken, that's the shrunken one, sorry. So where did, oh no, I must have started making that object. So, but those, we just had looked at that sheet, and it's gonna go and do that for the log fold change column in that sheet. Okay, and then, so let's run that so we can get this moving. Oh no. So yeah, this is going to take a while because of this log fold shrunken change here. So I'm going to keep going just to show you that really this is all the same thing. We're doing the same thing here. And in this first for loop, we're creating this res shrunken, but we first can populate this, and we're still in the for loop here. We can populate this temp res df, and that's what we're going to merge into these DFs up here. This is the temporary one. And we can say, take the results, which is currently just I, result name, make it as a data frame. This is the same thing we just did before, but it's going to do it for each result name. We're going to do row names to column, merge the gene names in, and make a new column called results name. And then for the res shrunken fold change, which is currently, you could see it was running for each entry in I as it went. And so it now has, the res shrunken has all of the information for each entry on the log fold shrunken change. And so to populate that one, we're really doing exactly the same thing. We take that object in the for loop that was just created, res shrunken, as a data frame, and do the same thing to format it. And then we can bind the rows of the res df and the temp res df up above. And the same for the shrunken res, will bind the rows of res shrunken df to the temporary, but the temporary one will be moved into the one we're going to keep in the end. So we want to pause and just go through that. It's really actually quite a simple for loop that it is running a function inside of it to create a log fold shrunken value. And so let's take a look at that real quick and say, let's do a res shrunken df. And what we see here is we have log fold 2 change, and we also have our log fold shrunken change here. And then for our res df, we just have the log fold change here. Okay, so now we can, depending on what we want to do, and we could actually just merge these two and get the log fold, shrunken log fold change in here. But I like to keep them separate for different things. Okay, so we can save that. And let's read in our nuclear and cyto results. And we're going to do some filtering and make a heat map here. So we can load in our nuclear versus cytoplasmic results from before, and we can make a filtering on that data frame that the P adjusted is less than 0.001, and that the absolute value of the log fold change is greater than 1. So that means it can go 2-fold down or 2-fold up. Either one it will take. So we can then filter that and call that sig genes. And then nuclear cytogenes to plot is going to be from the res shrunken DF. We're going to go into that DF now and filter the genes that are in the gene ID column of our SIG genes. So basically, the gene IDs that are in our nuc cyto SIG genes that we just made here is going to have a gene ID column. So we're just basically calling that column and saying that their results names are in these conditions, nuclear here and cytosolic here. So we're going into our res shrunken DF, and we're basically saying, give me only the values of those genes that were in my SIG genes from our non-log fold. So we filtered on the non-shrunken log fold change, and now we're subsetting in to get those log fold shrunken changes here. Okay, so let's grab those. And then if we're going to make a heat map, we're going to have to change it to a matrix. And let's take a real quick look at what we have with our nuc cyto genes to plot here. And what we can see is we got the fold change and the log fold shrunken change in both here for all the genes that were significant between nuclear and cytoplasmic. And we've plotted them before with the log fold change, and so we can see how the shrunken log fold change affects that. Okay, so now we are going to do make a log fold change matrix of those nuclear and cytoplasmic genes we want to do. We're going to select just these columns here, and then we're going to pivot wider, and we're going to take the names from the results and the values from log 2 fold change. So essentially now we're going to make a value for all the samples in plot the nuclear and cytoplasmic genes across all the log fold changes. Okay, so let's take a look at that step by step. So this, we're just selecting out the columns we want. So if we look at LFC matrix here, we just have the 3 columns: gene ID, log fold change, and result name. Okay, so that's handy. And now we're going to pivot wider on result name so that we're going to make a bunch more columns and basically end up putting the log fold change of each condition next to each other. So we'll have them all in one handy matrix. So if we look at that pivot wider here, we're now going to have a condition of log fold change for each condition, which we see here. We took the values. So we're only looking at nuclear and cyto. I'm sorry about that. But yeah, so we have now the log fold change for cytosolic versus total, and we have the one nuclear versus total. I see. So before we just did nuclear versus cytoplasm, and now we're comparing nuclear genes versus total and cytoplasmic genes versus total instead of just nuclear versus total together. So we ran DEseq to compare all the samples back to total. And so now we're going to compare nuclear and cytoplasmic differences with that comparison to total rather than just the comparison to themselves. Okay, and then we're just going to move the row names out here. So we have a matrix of these two, and we'll have nuclear and cytoplasmic genes relative to total log fold changes to plot. Okay, so let's run that. And then we can just do a heat map on this log fold matrix that we did, and where we see we just moved the gene names out. And so we just have a matrix with 2 columns for the 2 conditions of nuclear versus total and cytoplasmic versus total. Okay, let's see what we get. This can take a second, but this is where we will end. And let's see what we see. I don't want to export or zoom. Okay, so we can see that cytosolic versus total, these are the genes that are enriched in the cytoplasm. And if we look at nuclear versus total, we see that it's a different set of genes. So this is a different way, whereas before we were forced to find all the differences between the two of them. We're now looking at all the genes and saying, hey, are you enriched in cytoplasm versus total? And these red over here are enriched and these are depleted, whereas we see in nuclear, as we would have expected, that if you're depleted here, you would be enriched here. And so that's just a little bit different way of where we took all the results and compared them and made a data frame for all of our results, picked out these two conditions and compared them to total and not themselves. So just another way of running DESeq again, and it's worth sort of trying it a few different ways. And I think we got pretty similar results. So now what we could do, what we did before, is grab the genes that are cytoplasmic in this comparison and then ones for nuclear, and then overlap them with the nuclear cytoplasmic comparison and say, if you're true in both conditions, then you're really probably likely enriched in one or the other. So that's fun for you to explore on your own, and have now really done DESeq and gotten over the fundamentals, and now you're ready to go dig into the data and see what you found. All right, with that, thank you and be well.